right, everyone, thanks for the invitation. So I'm going to talk about work by students at Northeastern and the University of Amsterdam, where I'm based now. They are Heiko, Babak, Al, Sam, Eli, and Jared. And actually, 3 of these students are on the market this year, including for postdoc positions, both in the US and in Europe. So, if you're hiring, inquire within. All right, I thought I'd start things off, given that we've had a lot of talk about language models, and we've done some blind wine tasting with some blind model tasting. So here is kind of like a preliminary graph from a paper that we're hoping to send into the CHILL conference on Friday. What we're doing is we're predicting mortality from patient records, and we're comparing 3 models. I would like you to guess which model is which. Our model is flat T5, and we've augmented this model with some expert queries. We've asked the doctor to ask some questions you would like answered about the patient. We have the model predict the answers. We use the noisy answers for a classifier to predict mortality. And then there's 2 baselines. There's clinical BERT with the class token and good old TF-IDF. So maybe let's start. Who's willing to take a kind of wager on which one is our model?
Orange, because you're submitting the paper.
Orange, because I'm submitting the paper. All right, so Frank has an inductive bias. Yeah.
Say like purple because I want to be funny.
Purple because I want to be funny. All right, like some meta reasoning. So it is in fact the pink one. Or purple one, or whatever you want to call it. Like different people see colors different ways. AUC is still 0.8, which is not bad for healthcare, actually. And here, I guess there's a bit of a trade-off, right? So these expert queries allow you to kind of design your classifier in a particular way, make them a bit more interpretable, but I guess you take a bit of a hit. Okay, so these other 2 are pretty close. Anybody want to guess which one is BERT and which one is TF-IDF? I mean, I guess from science point of view, it doesn't really matter, right? But it turns out that BERT is the blue one, and TF-IDF, which actually gets the highest AUC in this particular example, is still standing strong in 2023. And, this isn't the first time this has happened to me working with my student Jared. Like TF-IDF in machine learning for healthcare can, in a remarkable number of cases, still be a strong baseline. Okay, so I'll use this as kind of like a motivating example to, I guess, start off this talk, which is mostly, I guess, a discussion. So I think what we're really seeing is that, there's been remarkable advances in scaling. And, like rich settlements bitter lesson has held up quite well. And I think the lesson is not that bitter. I think it's quite sweet, right? If we just train a model on all of the text that we can find on the internet, we do get some emergent kind of abstractions and generalization across tasks in ways that I think are quite surprising, right? And Sasha, for example, has, shown examples of this, just how much further these models have gotten. At the same time, I think the question that I'm interested in is, if you're trying to do a particular task, will your model do well enough on that task? And if it doesn't do well enough, what can you do? And it's still kind of hard to know when it will and when it won't. And I think kind of a good illustrative example that I've been kind of promoting is this blog post by Jacob Bachman, who's a student at my lab. And he asked the GPT-3 to play chess. So, you feed a prompt into kind of GPT-3, like a super intelligent chess agent is playing chess. Here are the first moves. And then the language model will suggest the next moves. And what's remarkable is this kind of sort of works. The GPT-3 will play some opening moves that are somewhat reasonable. Then pretty quickly the moves become less reasonable, and at some point they no longer are legal moves. And so I think this is both a win and a fail, right? Like it's remarkable that by just training on text on the internet, we can kind of sort of play chess. At the same time, the question from my point of view is, if we want to play chess, is this really the fastest way to get at a good agent for playing chess? Right, like, is there enough high quality data on the internet to give you a good starting point there? Or are you much better off doing something like self-play or some other solution that is more geared toward the specific task of playing chess? And so I think that's the question I would like to ask. How can we scale up AI, not only to larger data sets, more parameters, and it gets more compute and more people, but also to kind of a much more diverse set of application domains, and how do we get things to work for a very specific domain? Okay, so my slightly grandiose title is the next 700 domains in AI. And that number 700 is a pun, and I'll get back to that. So here's kind of like a sampling of domains that, are of course completely randomly picked and don't align with my interests or those of AmLab. So, you could work on things like, biophysics and neuroimaging, and we have done some work on this over the years. And you could ask the question, okay, what are the techniques you need here? And I guess what I found is that here often I've ended up working with generative models, deep generative models, variational inference, and later stochastic variational inference. Or you could consider domains like astrophysics. Maybe you want to infer kind of the presence of dark matter or the masses of black holes with gravitational wave measurements. Or you want to do epidemiology, where you want to predict kind of how many people are going to get infected. So here, I guess the ingredients we've discovered over the years are things like probabilistic programming, assimilation-based inference, and likelihood-free methods. I want to point to kind of a paper that Frank Wood's group wrote kind of early on in the COVID kind of pandemic. That was quite relevant here, and work kind of out of AmLab with Benjamin Miller and Patrick Foray, which is on neural ratio estimators, which is quite influential in astrophysics. But if I kind of think about the problems we're starting to work on, that's, I guess, what I would like to talk about. They involve things like molecular design. So can you design kind of a particular kind of substrate for a catalytic reaction? Things like material science. Can you design a metamaterial with certain kind of target mechanical properties? Or problems in fluid mechanics. Maybe you have, some fluid that's hard to describe, and you'd like to learn a differential equation from data that actually describes kind of the mechanics of those fluids. And here, in addition to kind of these ingredients that maybe we know and love, at least in this room, there's kind of like a new set of kind of technical problems that is emerging on the horizon. Things like Bayesian optimization and experimental design. How you design a surrogate model. So like if you have some expensive simulation, can you train a neural network to approximate the outcomes of these simulations? And how do you integrate symmetries and differential equations into kind of neural network-based approaches? And so I'll zoom in on one of these. This is a project in materials science. We are hiring for a postdoc. So again, if you're interested in working on a problem like this, inquire within. And so what we're trying to do here is optimize something called a metamaterial. So this is in this particular case, a metal structure that can be 3D printed. It has like a lattice-like structure. And here what we're doing is we're compressing this, and you see that it kind of folds in on itself in a very intricate way. And you could now ask the question, suppose I wanted to use this for a crumple zone in a car or something like that. How do I need to design this metamaterial so that it has the best kind of shock absorbing properties? And this spawns kind of like a whole set of sub-problems that I think are interesting and fascinating and very hard, and that we could be working on. Often you can simulate this stuff a little bit, but often you can only simulate it at a small scale. So you might have to train some form of model that you can simulate at a larger scale based on simulations at a smaller scale. This is called coarse graining. You might then want to say, okay, even if I can take that coarse grained model, I would like to predict some macroscopic response variables from kind of the initial conditions, and I may want to train like another neural network to kind of preempt that step. And ultimately, what you would like to do is you would like to say, well, I have many ways of constructing this lattice, and so there's a real kind of combinatorial kind of explosion of possible metamaterial designs. How do I pick the one that works best? And so here, maybe you'd like to do some form of Bayesian optimization in that combinatorial space. And so I think, like a lot of these problems are wide open. And I think that by basically picking a problem and saying, how are we going to make things work for this problem, you're often prompted to solve technical problems that otherwise maybe you wouldn't have thought about. And that's why I guess I'm excited about this class of problems. Okay. So I think one of the kind of classes of problems that I see come up again and again when I talk to collaborators are these kind of problems related to Bayesian optimization and experimental design. And here I would like to just point to kind of the work of Tom Rainforth, who also has some great kind of tutorial materials on this topic, and who I think is really one of the people that has arguably reintroduced this topic to our community as something worth working on. And so why does this pose interesting challenges? Well, you have this kind of cycle where you get some data, you use that data to update your estimate of what your model might look like. And so, we would think of that as approximating some posterior distribution. And once you've done that, you would like to pick the next experiment. And to pick the next experiment, you need to, imagine what data you might get. You need to kind of estimate how that data would affect your posterior estimate. And then you would have to pick the experiment that is most likely to reduce your uncertainty, or some other metric that you'd like to compute. And so at a very high level, if we're stepping back, you can formulate these things as a policy search problem. But really there's like inference as a subroutine here, right, in some design process. And that kind of motivates me to kind of get back to kind of why I called this the next 700 AI domains. So this is actually a pun. And my pitch here is going to be that, in order to work on these problems, we need some language abstractions that allow us to more effectively experiment with different inference strategies and different optimization procedures. And so kind of the next 700 AI domains is kind of a reference to this paper called The Next 700 Programming Languages by Peter Landon. This was written in 1966, so really the early days of computing. Or kind of programming languages, colleagues see this as one of the kind of seminal papers that really started off thinking about programming languages as a subject of study. And in this paper, Peter kind of says, well, when we have a programming language, and I'll paraphrase this very bluntly in a way that would make a programming language person laugh, you have two kind of components. You have some core operations, and you have some syntax for chaining these operations together into a program. And often when we think about a language, we think about the syntax, but really the core operations are what is at least as important in determining what we can and cannot do with the language. And so if you look at deep learning through that lens, right, there's really a lesson to be learned, which is that, differentiable programming has been this pretty flexible model. You have these core abstractions of differentiation and tensor calculus. And once you have these, you can basically start defining networks, you can start defining objectives, even kind of different optimization procedures, and you can start tinkering with this. And this has proved a pretty good mechanism for model development. Now, I, over the years, have spent a lot of time working on probabilistic programming, as is Frank. And, one way that you could summarize probabilistic programming is doing for probabilistic modeling what deep learning has done, differentiable programming has done for deep learning. And so here there's a different set of abstractions. There's distributions, there's conditioning on data, and there's applying inference to kind of the resulting model. And you get, some composition where, programs define stochastic simulators that you can define as, interpret as probabilistic models. Now, what I want to use the remainder of this talk to kind of point to is kind of the natural evolution that has happened in probabilistic programming, which is this domain called inference programming. I guess what we've kind of discovered in probabilistic programming is that if you need to get inference to work, sometimes you need to tweak it. And so what we've started doing as a community is design languages that allow you to write your own inference algorithms. And here's an example of such a language. Here's the syntax of the language. And each operation in this language defines a fundamental importance sampling operation. So for example, you could use samples as a proposal for another distribution, and then you basically increase or decrease their weights depending on whether they're overrepresented or underrepresented in the proposal. You can resample things, which means that if you have high weight things, you replicate them with probability proportional to the weight, and you get multiple copies, and maybe low weight kind of samples get eliminated, and you can move things around and update their weights accordingly. And so the thing with importance sampling is there's not that many of these fundamental operations, and you can design a grammar that has only a few terms that basically allows you to write down most important sampling algorithms that people use. And what you can then do is you can say, once I can calculate kind of the weights in this importance sampler, you can use that to define a variational objective. And now you have neural proposals, and these neural proposals you can basically train to optimize your importance sampler, and this gives you an amortized variational inference algorithm on steroids, so to speak. So this is out. It's being implemented in Pyro. It's been being implemented in Pyro forever, but I have good faith that it's going to happen soon. Heiko and Dufan, who is one of the Pyro developers, are on the case. All right, I'm almost out of time. So an example of something you could do with this is something that we call amortized Gibbs sampler. We've done this back in 2019, which were the battled days, I guess, by AI standards these days. Here, you have a video with some moving MNIST digits. You would like to be able to generate MNIST digits and detect where they are in the video. And in order to do that, you learn a Gibbs sampler. You learn something that updates the positions given the representations of the objects and updates the representations of the objects given the positions. And you can actually train this with this type of combinator-based language, and it converges in about 5 Gibbs sweeps and maybe 10 particles. So it's reasonably computationally efficient, and at the time, it was competitive with the most sophisticated LSTM-based approaches that people could devise for this type of thing in the VA. Now, that's not really my point in the context of this talk. In the context of this talk, I would like to talk about how do you develop something like this? And when we developed this algorithm, it took us 1.5 years, and then eventually what ended up in the algorithm block in ICML is this little squinty thing that you don't have to read. The point of this kind of algorithm block is that the individual lines here are things like sample from something, compute an importance weight, compute a gradient. And so if you get any of these lines wrong when you implement it, your algorithm is wrong, and it's very hard. It's wrong in a way that's very hard to debug. On this side is the same code, and it's about the same size, but now it's implemented using this combinator kind of framework. And the code is higher level. Right now, there's operations like take something and apply it as a proposal to something else. And all the importance weights and all the gradients are being calculated in the background. So now it's your job to figure out something that's efficient and is going to train, and that too is hard. There's another discussion to be had about that. But at least you're not going to have implementation bugs quite as easily, and so you can iterate over the space of possible inference algorithm designs more quickly. Okay, so I'll stop there. So I've given you a view of kind of how deep learning and probabilistic programming and inference programming are coming together. And I think that where this is mainly going to be important in the future is in these kind of experimental design and Bayesian optimization based settings. I'll stop there and I'll take some questions, and then I have some discussion questions for you as well.